So here's Gustav Kirchhoff. You see an image of him there at the top of the screen. I've teased you with Kirchhoff's loop rule and Kirchhoff's junction rule, but I haven't really formally defined either one of the rules yet. So let's get into Kirchhoff's loop rule. Kirchhoff's loop rule is actually a statement that follows from the law of conservation of energy. So let me start by making the analogy between a water circuit and an electric circuit. In the water circuit, a pump is used to take water and raise it to some higher amount of gravitational potential energy, right? The pump adds energy to the water. In the same way, the battery raises the electric potential. So this wire here, we'll say, is at ground, and this tank is also, we'll say, at ground level, so to speak. Yeah, so sure, the pump adds energy to the water in the same way that the battery adds energy to the electric charges that are in the circuit. So there's a current that represents a flow of water, maybe in gallons per minute or something to that effect. In the same way, there's a conventional electric current flowing in the circuit on the right. So there's a water wheel shown here that can take that energy of the water at higher elevation and convert it into some useful form. There's a transformation of potential energy into kinetic energy. And then all the water is back at ground level, but the pump re-energizes it, and on it goes. Likewise, the battery adds energy to the electric charges, but then the light bulb converts that electrical potential energy into light and heat. So energy is added by the battery, energy is consumed by the light bulb. Energy is added by the pump, energy is consumed by the paddle wheel. In any case, the amount of energy gained by the pump equals the amount of energy lost by the paddle wheel. The amount of energy gained from the battery is equal to the amount of energy lost from the light bulb. Now, instead of talking about the amount of energy, we could talk about the amount of energy per unit charge. In other words, the number of joules per coulomb, but that's a volt. So to say that the energy gain equals the energy lost is the same thing to say that the voltage gained equals the voltage lost. And that's really Kirchhoff's loop rule. So we'll state it mathematically like this. The total change in voltage all the way around a loop, either counterclockwise or clockwise, we can just write the word loop. The total change in voltage around a loop is equal to 0, which is equivalent to saying the total voltage gain is equal to the total voltage loss. And we can think of voltage gain as coming from the batteries and the voltage loss across the resistors. Now we've got to be clear about how we calculate voltages. So typically what we'll do is make a reference point, pick some point along a loop that we want to define as electric potential equals 0. So here you see the symbol for ground, so we're defining electric potential equals 0 at the lower left corner of this circuit. From there, we choose whether we want to trace our way around this loop in a counterclockwise direction, or if we want to trace our way around that loop in a clockwise direction. Now, I'm not representing the direction of the electric current with these loops that I'm tracing. I'm just stating how I'm going to, in my own head, go from point P back to point P. And I can trace my way around the loop clockwise or counterclockwise. Depending on which way I trace, I'm going to encounter batteries in different directions. For example, if I trace my way around in a counterclockwise direction, then for the 10-volt battery, I'm going to encounter it from its negative terminal toward its positive terminal. Of course, that sounds like a gain, right? To go from negative to positive is a gain. However, eventually, as I continue tracing around counterclockwise, I'm going to get to this 60-volt battery, and I'm going to encounter it from its positive terminal toward its negative terminal, right? And that sounds like a voltage loss. So to generalize, the way we calculate voltages across a battery, if we're tracing our way along a circuit and we go from positive to negative, that's a loss. As we trace our way through a circuit, if we go from negative to positive, that's a gain. Okay, now how do we calculate voltages across resistors? Oops. Yeah, how do we calculate the voltage across a resistor? After all, a resistor doesn't have a defined positive and negative side to it. It really depends on the direction that current is flowing through the resistor. So let's say we have a resistor whose value we'll just say is R, and we know that the current is flowing to the right. So as we're tracing our way around, remember we can choose to either trace our way around a loop in a counterclockwise direction, or we can trace our way around in a clockwise direction. Anyway, if we were tracing along counterclockwise, so we encountered this resistor in this direction, then we're encountering it opposite the direction of the current. You can think of it as like swimming upstream, if that analogy works for you. So that would represent a gain in voltage. Given that same resistor and the current is flowing to the right, if we were to encounter that resistor as we traced our way around a loop in a circuit in the same direction as the current, then that's like swimming downstream, and you can think of that as a loss in voltage. Okay, so with all that in mind, let's see if we can figure out, for example, the question might go, what's the electric potential at point X? Okay, so gosh, let's just guess which direction the current flows. Now it'll be a bit of an educated guess. Look, the 60-volt battery is the greatest potential difference of all, right? And so we would think that in and of itself, it would drive an electric current in a clockwise direction. However, the 20-volt battery has its polarity in the opposite direction. It would want to drive a current this way, but it's not as much voltage as the 60-volt battery. Likewise, the 10-volt battery would also have a tendency to drive a current in a counterclockwise direction. But again, even if I added the 10 volts with the 20 volts to get 30 volts, that's not as much as the 60 volt. So if you want to go back to the water circuit analogy, it's like I have pumps facing in opposite directions. However, these two weaker pumps, so to speak, don't add up to be powerful enough to offset the effect of this pump. Yeah, so I feel pretty good in guessing that the direction current flows in this circuit is in a clockwise direction. So let's see what happens when we trace our way around the circuit, also in a clockwise direction. Okay, so starting at point P, the first change in electric potential we find is due to tracing across this battery from its negative to its positive terminal. So we're going to say plus 60, and then we encounter a resistance of 6 ohms. So we're tracing our way in the direction of the current, so that's going to be a loss in voltage, and we find that by multiplying the current times the resistance, although I'd rather write that as 6I instead of I6. So 6 ohms multiplied by a current. We don't know the value of the current yet, so the best we can do is just call it I. Okay, the next thing we encounter is a 20-volt battery, but on that battery we're going from the positive to the negative, so that's a loss in voltage, so we'll say minus 20. And then we encounter a 12-ohm resistor. Our tracing is in the same direction as the current, so it's a loss in voltage, so this is minus 12I. Okay, then we encounter a 10-volt battery from the positive to the negative terminal, so minus 10 volts. And again, we encounter 2 ohms of resistance. We're tracing in the same direction that current is flowing, so minus 2I, and that brings us to point X. All right, let's continue tracing all the way around, though, back to point P. So the last thing we encounter is a 20 ohm resistor. We're also tracing in the direction that the current is flowing, so this is minus 20I. So we can combine like terms, minus 6I, minus 12I, minus 2I, and minus 20I. So that sounds like minus 40I. And we have 60, minus 20, minus 10. It sounds like 30. And that brings us all the way back to the point where we started. So what we're really saying is all of this represents the net change in voltage, but by Kirchhoff's loop rule, that has to equal 0. So this means 40I has to equal 30, so I is equal to 3/4 or 0.75 amps. All right. Now, what if we had traced in the other direction? I think we were correct in guessing that the current flows clockwise, because after all, our answer came out to be positive 0.75 amps. Now sometimes we just guess the direction of the current, and if we work it all out and in the end we find that the current is negative, then that just means we guessed the direction wrong. So for example, had we guessed to start with that the current flowed this way, our answer would have been negative 0.75 amps, but then we'd keep this our secret, right? We wouldn't tell anybody. We'd just say, well, no one was watching. No, I really had the current this way, and then I'll change the negative into a positive when no one's looking, and nobody will be any wiser. Okay. Let's trace our way from point P around the circuit back to point P. In this case, the first thing we encounter is the 20 ohm resistor, but we're tracing opposite the direction of the current, so that's actually a voltage gain. So this would be plus 20I, and then we'd have, again, plus 2I, right? We're tracing counterclockwise, but the current is flowing clockwise. And then we're going from negative to positive, so plus 10, plus 12I, plus 20, let's see, is this plus or minus 6I? So we're tracing in this direction, but the current flows in this direction. We're swimming upstream, so to speak, so yeah, it's plus 6I. And then lastly, we're going from the positive to the negative on the 60 volts, so minus 60, and according to Kirchhoff's loop rule, that all has to equal 0. When we combine like terms, we get 40I minus 30 equals 0. 40I is equal to 30, so I is equal to 3/4, which is positive 0.75. Positive because, yeah, we guessed the direction of the current correctly. Okay, so it doesn't matter which way we trace our way around a circuit. It doesn't change the answer. It just changes how we assign the positive and negative values in our statement of Kirchhoff's loop rule. Back to the original question, what's the electric potential at point X? So we could go the long way to get from point P to X. We can go across all these devices, or we can go the short way, which just goes across one device. Okay, so let's see. Let's go the short way. We know the current goes in this direction and is equal to 0.75 amps. So to go from point P to point X, we trace to the right, which is opposite the direction of current. So if the electric potential right here is 0, then the electric potential at point X should be higher by a value equal to 20 ohms times 0.75 amps, or 3/4 of 20 if you prefer. So the electric potential at point X, I believe, is 15 volts. Now let's see if that's the value we get when we trace the long way from point P to point X. So as we go the long way from point P to point X, we're tracing around the circuit in the direction of the current. So starting at point P, we have an electric potential of 0, and we add to that a potential difference of 60 due to the battery, and then we subtract from that, because we're going downstream in the direction of current, minus 6 times 3/4, 6 ohms times 3/4 of an amp to be more specific, minus 20 volts, because we go from positive to negative, minus 12 times 3/4, minus 10, minus 2 times 3/4. So we have 60 minus 4.5, minus 20, minus 9, minus 10, minus 1.5. Let's see. Call that 11.5. Call that 20.5. Call that 40.5. Call that 45. Oh yeah, so we have 60 minus 45, which lo and behold is equal to 15. Okay, so there you have it. No matter which way you trace a path around an electric circuit, Kirchhoff's loop rule seems to hold up. The net change in voltage all the way around a loop is equal to 0. So the net voltage gain is equal to the net voltage loss as long as you come back to your starting point. If you don't come back to your starting point, then there's going to be a net difference in voltage, and the way we calculate those differences depends on which way we encounter the resistors and which way we encounter the batteries. If current is flowing to the right in this resistor, then if we trace our way to the right, we're going to have a voltage loss. If we encounter a battery from the negative to the positive terminal, tracing to the right, that's a voltage gain. However, had we traced to the left, then there'd be a voltage gain across this resistor, and there would be a voltage loss across this battery. Hopefully that gives you more insight into Kirchhoff's loop rule. Bottom line, Kirchhoff's loop rule follows directly from a statement of the law of conservation of energy. Really, it's conservation of energy per unit charge, and energy per unit charge is voltage. This is why the net change in voltage all the way around a loop is equal to 0.